Okay, let us move ahead on inferential statistics today. Okay, today I'll cover some essential concepts that form the backbone of inferential statistics. Okay, by the end of this session, you will understand the what and why of inference statistics and what is population and sample and sampling distribution, central limit theorem, confidence interval and confidence level, and so on. Okay, so let's get started. The first thing first, what is inferential statistics? What is inferential? Why do we need to use inferential statistics? So as I said earlier, the very first session, there are two branches are there in statistics. One is the descriptive statistics, other one is the inferential statistics. Within the descriptive statistics itself, we have seen the central tendency, measures of central tendency, and we discussed about measures of dispersion. In statistics, there are two branches. One is the descriptive statistics, and the other one is inferential statistics. In descriptive itself, there are two branches. One is the central tendency, measures of central tendency, and the other branch is measures of spread. We discussed about the measures, the mean, median, mode, and the range, standard deviation, covariation, and so on. And now let us proceed with understanding what is inferential statistics. Why do we need to use the why inferential statistics came into picture? What is the advantage of inferential statistics? What is inferential statistics? It is a branch of statistics. It involves using the sample data to make inference or draw conclusion. One second, yes, there is problem here. Please remember that in the real world scenario, you will not get access to the entire population all the time. Most of the time, you will not have access to the population. Even if you have access to the population, it will take time. It is a time-consuming process to take the entire population and making inference about the population. It takes time. Collecting the data itself takes longer time. Even if the data is available, it's a time-consuming process. And most of the cases, right, you will not have access to the population data at all. That is when the inference statistics coming into picture. I don't have access to the population data. Is it possible for me to make an inference about the population? Yes, that is possible using inference statistics. It helps us to generalize our findings beyond the observed data and make prediction or test hypothesis. Okay, it make inference about a population based on a sample data. It's as simple as that. The goal of inference statistics is to use sample data to estimate, right? I'm going to rephrase my statement, okay? Estimate the unknown characteristics of a larger population. First of all, I don't know what is the average height of the students in a college. Let's say in a bigger college, like Satyabama College or very, other colleges, right? Ishwar Engineering College. You have 10,000 or, 50,000 students are there. Let's say even the case of final year students, if you want to find out the average height of a student or average age of the student, the final year student, it is difficult. You need to measure each and every student's height. It's time-taking process, and also they have different branches, right? You need to go to different locations. So it's a time-consuming process. Is there any way that I can, make a, inference about the population with the sample data itself? Yes, that is where the inference statistics is coming to picture. Using the sample data, you can estimate the unknown characteristic of the larger population. In my example, in the 10,000 students are there in the final year. Let us assume that the BE computer science final year students, 10,000. Let's assume that, okay, hypothetically, okay. So 10,000 students are there. Is it possible for me to find out the average height of the final year student. It is difficult. It's time-consuming process. Is there any way, can I use my sample to make an inference about the population? Yes. Using the sample data, you can estimate the unknown characteristics of your population. Look here, this is what your population. All the students are there in a college. Okay, this is your college students. 10,000 students are there. And but you don't know what is their average height. Average height of final year students. You don't know what is the average height of the final year students. Okay, is it possible? Let's say you draw a sample and you run a survey with, let's say 40 to 50 students, and you measure their height and you note down each and every person's, right? Your sample size is 50. So we always say we always use a notation called N, right? We always use a notation called N. N is the sample size. N is equal to 50 students. Because measuring the height of the 1,000 students are time-consuming process. Instead, what you do, randomly, you are calling 50, you are measuring 50 final year students' height. Okay, this is your sample. I call sample mean. I call the sample mean as X bar. Population mean is mu. My population mean I don't know. Mu is population mean. X bar is your sample mean. Yes, you have 50 students height with you because you measured each and every student's height. Ashik, what is his height? And what is Jayashree's height? And what is Jay Prashant height? What is Jivanandam height? And what is Leela height, right? Like as you measured each and every student's height, the 50 students height, but you randomly selected 50 students from the final year students, and then you computed the average. Since you have the data, you can compute the average. With this sample mean, it is possible to estimate the population mean. So here I use the term estimate. You can estimate the population mean, right? Using the sample mean, you can estimate the population mean. So what do you mean by estimate? Estimation is something like, we are making an estimation, right? It involves some kind of degree of uncertainty. It is not, exact, value. For example, the 50 students average height is 174 centimeter. This is for the sample, the random sample of 50 students, final year students height is 174 centimeters. So the average height for this sample, 170. With this, just because 50 students average height is 174 centimeter, can I conclude that my population, all the 10,000 final year students height is also on an average of 174 centimeter? Can I conclude that way? That is why we are using the term called estimate. There will be some kind of variation. Right? That we will discuss it a little later. But this is the whole idea of using the inferential statistics. Using the inferential statistics, we are going to generalize our findings beyond the observed data and make predictions, or we can make an estimate of our unknown population. So why do I need to use inferential statistics? It allows us to work with smaller sample. Like I said, working with the entire population is meaningless. Okay, so if I want to find out the customer's purchase behavior, if I run if I call each and every person who lives in India, it doesn't make sense, right? People will laugh at us. So what we do is you take a sample, smaller sample, using which we are going to make an inference about the larger population. That is where the inference statistics plays an important role. But the question is, like I said earlier, the average height of the 50 students in my sample is 174 centimeter. With that, can I say, by closing my eyes, all the 10,000 final year students in my college, their average height is also same as my samples mean? No, right? there will be, variation. There will be how are we going to define that variation? Right. So that is where this inferential statistics comes into picture, and we have something called central limit theorem, everything, which we are going to learn it little later. Okay, as I move further, your understanding will evolve. Hence, I would suggest you all to please focus here. Now the question is, what is the difference between descriptive statistics and inferential statistics? It's pretty simple, straightforward. Using the descriptive statistics, we can summarize and describe the data. It gives us the gist of what is, this 5-number summary. Somebody is asking you 5-number summary. What is the minimum sales? What is the maximum sales achieved by my sales team? What is the average sales achieved by my sales team? What is the upper quartile value? What is the lower quartile value? You can give 5-number summary. Or maybe 6-number summary. You can give mean also, mean, median, mode. You can give all the things, right? That's all. Okay, you can tell the average sale is, let's say the average sale is 70K. But can you conclude that the average sale, just because, in a specific sales team, let's say you have 5 different sales teams are there. Each sales team, they have 50 salespeople are there. 5 into 50, 250 salespeople are there. Just because, you take an average of one specific thing, can you generalize all the 5 sales team, all the 250 sales team, all the 250 salesperson put together on an average, they achieved 70 K? With descriptive statistics, you cannot do it. That is where the inference statistics is coming into picture. Using inferential statistics, you can make inferences about a population based on a sample data. Another thing which you need to keep in mind is the descriptive statistic can be used with any type of data, whereas inferential statistics you can use only with quantitative data. If you remember this much, that is more than sufficient. It's a very simple concept. And these are the terminologies you need to remember it. For example, I have a population. This is my population. And let's say you have different values are there. Different values are there in the population. What you are doing is you are taking a subset of the data. This is your sample 1. Sample 1. So for the sample, let's say you have taken 3 values. Let's assume that these 3 values are 3, 8, and 4. Instead of saying, 4, okay? 4. In this, sorry, let's say 5. You will take 5. Okay. In this case, what happens? What is the average? If you find out the average for this sample, how much you will get it? So 13 plus 3, 16. Right? 16 divided by 3. Okay. And what I will do is I'm going to put another number. Here I just put 5 here. 5, 5, 5. And here, let's say 5, 5, 5. Right? Let's assume that all 4 5s are there. 20 divided by 4. Okay, you get how much? The mean is 5. This is called your X bar. The mean, the sample mean is called X bar. And the population mean is called as mu. Mu is the parameter. The mean, the sample mean is called as a statistic. The population mean is also called as a parameter. I'm going to now, I just go back to my previous discussion. So here, in this case, using this sample statistics, which is mean, sample mean. So we are going to estimate the population mean. We are going to estimate the population mean because you will not have access to the population data, first of all, in most of the cases. You are running a survey with a few people, and that is your sample. With that sample, you are, since you have the data, because you ran a survey with, let's say, 50 students in this case, you have the data with you. With that, you can find out the average. But the population, can you find out the average? Very difficult. Okay. So using the sample statistic, we are going to estimate the unknown population mean, which is nothing but mu. The statistic and parameter, you need to be familiar with these 2 terms. If you are going to be familiar with these 2 terms, nothing is there. Okay. The sample mean is called X bar, and the sample standard deviation is called S, whereas the population standard is sigma. And if you square this one, that is what your variance. If you square the population standard deviation, that is called a variance. And the size, the sample size is again. Okay, so we use the term N to represent sample size, population size capital N, proportion small p, and pi. This we'll discuss it later. Correlation R and P. Up to this, if you can understand, that is enough, if you remember it. So all these sample related measures, we can say mean, standard deviation, variance, and size. We use this notation. These are called your statistic, and these are called your parameter. Anything related to population, we call it a parameter. Anything related to sample, we call it statistic. These are the 4 different types of statistics. If you remember, that is more than sufficient. These are the 4 parameter, population parameter. If you remember, that is more than sufficient. Okay, I hope all of you can remember it, because it's very simple to remember. You have space in your brain. I hope you can remember it. Next, we will understand what is population and sample. So, okay, what is population in statistics? Statistics different from statistic. This is different, guys. Okay, statistic, which means they are talking about sample. Okay, statistics is the one which we are learning it now. So, what is population? Can someone tell me what is a population? Population is you, me, everybody in this world, all the humans in this world. We can say that is a population. All the living beings in the world is called your population. The universe, right? The universe, everything is in the universe. That is your population. The population refers to the entire group of interest that we wanted to study and draw conclusion about. Okay. So what do you mean by the entire group of interest? For example, the population of all students in a particular high school. Another example is the population of a retail store, wherein you have all of the customers who shop at the store in a given year. You are very particular about your interest is your interest. Yes, you want to conduct a research. You want to conduct a research. As part of the research, your area of interest is you want to see, within this, for a specific given year, which all customers, they shop, how much money they spent. Money spent by all the customers in a specific year in my shop. Okay, that is your population. So population refers to the entire group of individuals, objects, events that share a common characteristics. And also it refers to the entire group of interests that we want to study and draw conclusion about. That is what your population. Okay, we can make inference about a population based on a sample of the data. That is what I already discussed. And okay, what are the examples for population? All college students in Tamil Nadu, or all college students in Kerala, or all students in India. This is population. Again, it depends on the area of interest. Let's say I'm interested, interested in studying. My group of interest is all college students in Tamil Nadu. This is my population. I take the population, I draw in Tamil Nadu, I'm going to randomly conduct some survey, and then I'll get the heights of the students, and then I'm going to generalize the population height. Okay. And the next one is the all smartphones manufactured by a particular brand in a given year, and all car manufactured by a specific car company, and all households in a country, and all first-year college students in Anna University, population of all employees in a company. Let's say you work for TCS or work for Accenture. So you want to understand, you want to run a study, right, with all first-year college students in Anna University. Then your area of interest is the first-year college students. So you are taking all the first-year college students in Anna University. That is your population. Next one is, what is sampling? What is sampling? Sampling is a subset of your population, a representative subset of the population. The sample must be random and unbiased. Please remember this. Random and unbiased. It should be a representative of the subset of the population. The sample must be random and unbiased. So what do you mean by representative subset of the population? When you draw a sample, it should cover all the groups. Let's say a simple example is you are running a survey. You have someone like, in your population, let's say in your population, you have high income group people, medium income group people, and low income group people. If you run a survey only with high income group people, and then you can make a decision that all the customers average spend on a year is, or on a month is 1,20,000. Can you draw a conclusion like that? If you draw a sample only from a specific group of people, especially one specific group, in this case, high income group people, your sample is biased. Your sample is biased. It is not a representative of your population. Make sure that you are running a survey with low income group people, medium income group people, high income group people. Only then we can say that your sample is a representative subset of your population. You are covering all segments of the customers with different income group. But you are, running a survey with one, randomly with, each group customers. So hence it is called random. It should not be like specific customers, right? It should be randomly, so that it will be unbiased. You randomly run a survey across all the groups. Your sample will be unbiased. So your sample is supposed to be a representative subset of the population, and it should be random and unbiased. Okay, the next question is, why should I, what are the examples for sample? Yeah, what are the examples? Give me some examples. The random sample of 150 students in a college, a random sample of 100 smartphones from a latest model released by the brand, random sample of 1,000 households from urban areas across the country. Likewise, right, we can take a random subset of the data from a sample, from a population. That is what your sample. Other example is, okay, I'll just come back to that simple example. So now the question is, why do I need to sample the data? Why do we, like I said earlier, it is very difficult to get access to the population data in the first place. Okay, hence we need to rely on this sample. The reason why we need to sample the data is it is cost effective and it is not going to consume much time. And so if you rely on the population data, right, it is impossible to collect the entire data. If you want to take the entire data, it is highly impossible. That is also a reason why we need to sample the data. If you take the entire population, time consuming, and it is highly impossible, and it involves too much of cost because you need to put more staffs to gather the entire population data. So for that reason, we have to do the sampling. The question is, how do we sample the data? That's what I said. The sample must be a representative population and it must be unbiased. Okay. So the advantage here, the sampling can save cost, human and other resource cost. The disadvantage may not be representative. So we can run a survey with a different set of people, but still, we cannot say that it is a representative, right? It doesn't, the sample survey, whatever you ran it, the data, what you have in your hand, it cannot be representative all the time. The simple example is, for example, you host a party in your house. You want to buy sweets. You visit a nearby stall, right? Sweet stall. Okay, you go to a sweet stall and then you want to buy sweets. What you do is you first ask them, give me some, you want to buy 2 different or 3 different varieties of sweets in bulk. So before you buy it in bulk, what you do? You take a sample, you ask them to give a small piece in, these three different varieties, and then you taste it, and then you generalize how the quality and taste of these three different varieties of sweets, and then only you are going to buy. Using the sample, you make an inference about this, huge quantity of each variety of sweets, right? So the same thing is applicable here. But here, what you do is you go and you want to buy three different varieties of sweets. What you are doing is you are, getting this sample from three different sweets. Hence, your sample is a representative of this population. What if you get a sample only from this sweet, and if you decide the rest of the other two sweets also same as this taste, and if you close your eyes and order all the other two items also, what is going to happen? There could be chances, it may not be as good as this one. Hence, what you do is you draw a sample from each and every, item of these three items. You take samples, and then you taste it, and then you decide. The same idea is applicable here also. So instead of, my sample should be unbiased, it should be random. So how can you make sure that my sample is unbiased? It should be random, right? See, in the case of the similar example, let's, in the sweet stall, right? You want to buy three different sweets in bulk. You are going to, get this sample, right? Give me a small sample in all these three varieties. But you ask them, hey, in this one, you give me the, sample from this side and this side. Don't give me from here itself. Okay, give me this one. The classic example is fruits, right? Before you buy mango fruits, you want to buy it in, 50 kgs, 50 kgs. Right? They give one sweet, and here also say one fruit. But when they pack it, there could be, so what you do is, don't give me this one and give me something, here and there. Right? I want to see it. So the representative, and it is random. You want to do not in a specific place. Maybe, the outside, it may look good, but, just, beneath the heap, there are some fruits it would have got, spoiled, right? So in that case, you want to make sure that all the fruits are in good shape. You sample that data randomly, but you sample from three different varieties. And at the same time, randomly you are going to sample it. Hence, your sample is unbiased. And also, it is a representative population since you are collecting from three different varieties. That's it, guys. If you understand this one, you're all set. So your sample is supposed to be a representative population. It should be random and unbiased. If you sample it randomly, it is going to be unbiased. What are the different types of sampling techniques are there? So there are different sampling techniques are there. So at a high level, there are two branches. One is the probability sampling technique and sampling probability technique, or non-probable sampling technique. Within the probability itself, we have 4 different types are there: simple random sampling, stratified random sampling, cluster sampling, systematic random sampling. And in the case of non-probability sampling, you have the convenience and quota sampling. I wouldn't recommend these two because it is very time data. Okay, we work most of the time with the real-time data. Once again, okay, hence, this is not recommended one. So let us take a look at, or let's dive into each and every type of these sampling techniques. To start with, let us understand what is simple random sampling. So this is your population. Okay, so in your population, you make sure that you are picking up every item in such a way that it has an equal chance of being selected. Every item in a population chosen in such a way that every item has an equal chance of being selected. That is what your simple random sampling. Okay. So in this case, what are the advantages? Easy to draw unbiased. Easy to draw because you close your eyes, you randomly sample here and there. See, if you could have seen the television program, right? So there are some kind of program in a television. You might have seen this one. There will be some competition. two different people will be, arguing, or, they participate in the contest. At the end of the contest, right, they will ask them to come and shuffle all the papers. They write each and every person's name in a paper, and then they fold it, and then they put it in a big jar. And then they ask them to come and shuffle it first, right? Why do they need to shuffle it? So that every item or every person name should have an equal chance of being selected. That is the reason why they're shuffling it. Okay. And then you randomly go and you call some people in the audience, from the audience, and ask them to close their eyes, and then pick up 3 or 4 papers or sheets from that thing, folded sheet papers, right? All ask them to pick it. That is what your simple random sampling. So if you shuffle it, what will happen? Every item in a population, has an equal chance of being selected. That is what your simple random sampling. But when you close your eyes, right, randomly when you select it, what will happen is it may not be representative. It may not cover all these segments. Like in the previous example, high income group, medium income, low income group. If you close your eyes and pick up the thing, right, there could be chances you might be picking up the people name from the high income group only. Hence, it may not be representative. There will be a huge variance, but very easy to draw. Hence, it is unbiased because you are closing your eyes and it is got shuffled already. To make sure that everyone should have an equal chance of being selected, you're shuffling it. You close your eyes and you randomly pick up. Very easy to draw. It is unbiased. If I don't, close your eyes, what is going to happen? And again, only 10 contestants are there. What is going to happen? There is a question, how does the sample is being identified? I mean, the type of sample being required. That we'll discuss it later. First, let us understand the pros and cons of each and every type of sampling. Then you will understand what sampling technique is, what sampling technique to be used when. Okay. Supposing you don't have, much, your volume of the data is very, very huge, very, very huge. In that kind of situation, and again, you need to make decision quickly. You don't have time to draw even the huge sample. And again, you don't have access to the entire population data. Then you are left with simple random sampling technique only. Obviously, it has some kind of bias with it. Okay. But you need to, you need to specify the assumption saying that, I don't have access to the population data and all segments of data also, I don't have access. Since given the time constraint, we have used the SRS technique, simple random sampling technique. It's a good question, okay? And next one is stratified random sampling. So every group is represented proportionally to its relative size in population. For example, this is what your population, and you have 3 different groups of people out there, okay? So here, in this case, how do we draw the sample? So we have divided this entire population into 3 different groups. For example, this group of people are having an affinity towards a specific Samsung brand, and these people are having, a very affinity towards iPhone, and these people are what other brand? We have something like Motorola or something like that, okay, Motorola, or the MG, right? Samsung, MG, or iPhone. So these people are having, brand affinity. What you are doing is you are going to draw a sample from all these 3 groups. Your sample should be a representative of the population. In the case of stratified random sampling, what we do is we draw a sample from all the groups. How do we draw the sample from? The next question, how do we draw a sample from these 3 groups? Can I draw here 1, 1, 1, or can I draw 5 and 5 and so in this case, each group is represented proportionally to its relative size and population. Relative size and population. Supposing you have, for the sake of simplicity, let's you have 10 customers. Let's 10 customers you want to randomly sample it. Your sample size is 10. But your sample is supposed to be representative. What do you mean by representative? You need to randomly sample the customers from all the 3 groups. Okay, in this case, here I have 5 and 3, 8 plus 2, 10. Can I say 5, 3, 2? 5, 3, 2. So let's assume that, let's say you have 100 customers are there. Let's, here you have 100 customers, out of which 50 customers are Samsung and 30 customers are iPhone, they are MG, and 20 customers are iPhone. Okay. So your sample size is 100. Okay. Out of which let's assume that this is your population size. Okay. So this is your population. In your population, you have 100 customers are there. 50 customers, they bought Samsung, and they have more affinity towards Samsung brand only. Okay. They may hold more than one mobile phone, but all the mobile phones belongs to Samsung. The same customer, he may be having more than one Samsung brand he bought it. Okay. That's how brand affinity, in the sense these customers, they are very particular with Samsung only. Okay. So if I ask you to draw the sample with size 10, what proportion you are going to draw the sample from these three groups? 10, right? So out of 10, 5, 3, 2. Because you have more people, right? So 5, 3, 2. So in this case, with the proportional sample, so sorry, with proportion to the population, right? The sample also should have the proportions of your population, or in other words, the sample should have the proportions similar to that of your population. Here 5 is to 3 is to 2, right? 5 is to 3 is to 2. So that is how we need to draw the sample. Your sample should be the proportion of your population's size. Okay, the sample size should be proportion of your population size. Okay, that is what called as stratified random sampling. Okay, and the question is, okay, is it always mandatory? They said there are some cases my group is represented disproportionately to its population. So in the previous case, yes, let's say you have 500, 300, 200, but here if you see 200, 400, 600, 800. With the disproportional sample, the sample need not to have the same proportion as your population. Need not to have the same proportion as your population. Supposing if I ask you to draw 10 samples from this population, what will happen? If you go by the proportion, here if you draw 8 and 6, 4, 2, what will happen? Here, if you see, very less number of customers are there, right? You have very less number of customers. Your sample size should also be reasonably good. If it is very less, then your outcome will be whatever the test that you conduct with the sample that have less number of data in it, it can lead to some kind of bias. Okay, so with the disproportional sample, with disproportional population, the sample need not to have the sample, your sample need not to have the same proportion as the population. So you can, in that case, you need to use your common sense, right? You need to use your common sense. So if somebody is asking you to draw a sample, something like, 10 or let's say 20, if they ask, right? You can tell them 10 is not possible. It is going to be, very small samples. So let's say if they ask you, let's say 100 samples, you can make sure that you have reasonable amount of people selected in this group also. Like I said, in simple example, 10, if you 8, so let's say 20, right? 8 plus 10, 20. So your sample size is 20, but in this population, you have selected only 2. This sample size is very small. In this group, you've taken very less number of customers. Obviously, it can, it will have a bias towards the higher values in your sample, right? So make sure that in the case of disproportional sample, you need to use some kind of common sense, and then you need to draw the sample. For example, your sample is 100. Make sure that in this population you are drawing more. Okay, listen, here you are going to draw at least 50 and 40, and here you can say let's say in this case 20. Here you 20 and 40, right? So 40, 60 and 20, 20. Okay, here you can 20, 20, something like that. Okay. So it should be reasonable. If you put 2 here or 4, very less, right? Make sure that each group also have reasonable amount of samples in it. The sample size are too small, your test result, statistical test will not give you it will mislead you, your sample test output. One second, please, I'm getting it. Drawing sample across all the group. Whereas here, in the case of simple random sampling, you are closing your eyes, or in simple term, right? You are randomly sampling the data, right? Randomly sampling. When you randomly, it's something like you are closing your eyes and picking up the items from or objects from this sample in the population. In that case, what will happen? There could be chances you might miss out some specific segments data while sampling it. So hence you tell me which one is good. In most of the time, the stratified random sampling is the one we do it. Okay, this is the one is advised one. And there are some situations you don't have access to all the 3 groups. Then you have to go for SRS, simple random sampling. The next one is the cluster sampling. What is cluster sampling? In the case of cluster sampling, we divide the whole population into groups like stratified sampling. Here also we are going to divide the entire population into clusters or groups. Groups also called as clusters or clusters, okay? And even in this case, a random sample of cluster is selected. For example, in this group, in the population, there are 2 different groups of people. These people always prefer Samsung and these people always prefer iPhone. Or, okay, this is not the correct example in this case. Okay, what we will do is, what we will do is we'll take the high school students in a large city. Okay, instead of selecting individual students from all schools, we will randomly select a few schools from different regions in the city. So this is your north region, and or there's some group of schools. Let's or the area. Let's this is your entire Mylapore, and this is your Adyar. Okay. Instead of selecting individual students from all schools, we randomly select a few schools or clusters from different regions in the city. Then you collect data from all students within the selected schools to represent the entire. So in this case, simple thing is we have one more cluster is their group, and these people are from Aryapuram. These people are from Besanagar, Adyar, these students, right? Okay, schools, group of schools. It's not an individual school. Group of schools in Besanagar, group of schools in Adyar, group of schools in Mandeveli. What you do is you divide the entire problem into groups and randomly select any one of the cluster. So these are groups are nothing but clusters. Okay. So I'm going to randomly select this one, Mylapore. Okay. Or maybe randomly I can select this one, or I may randomly select this one also. You select any one of the, divide the population into groups, and then you randomly select a cluster. And then what you do is you run a survey, or you collect data from all students in this cluster. In Mylapore, you collect data from all the students studying in all the schools. All the students from your Mylapore. Okay. So instead of going and collecting the samples from each and every schools or each and every individuals from each and every school, what you do is you create a cluster or group. In this cluster, all the schools in Mylapore, all the schools in Adyar, all the schools in Besanagar. And then what you do is you take any one of the group randomly, and then you run a survey with all the people in that specific cluster. This is what your cluster sampling is all about. Now the question is, when can I use the cluster sampling? So what is the advantage of this? What is the disadvantage of this? So here also there could be chances when you create a cluster, it may not be representative of your population. Okay. Another aspect is, right, if you think collecting the samples from all the students from all the schools in all the locations is very costly prohibition, right? Cost wise, it is highly prohibition, right? So in that kind of situation, you can go for cluster sampling. If the cost is too high, so this is a simple way of doing it. The other simple example is, for example, you are running a hotel somewhere in a holy place, somewhere in the, let's say, the holy place, right? Holy place. A temple is there, and a specific event like Masi Magam. I guess all of you people are familiar with this festival in Kumbakonam, right? In Kumbakonam, this festival will happen. So that time, a lot of pilgrims, they throng this temple, Kumbakonam temple, take a bath, right? So in that case, let's you have a hotel there. It is a 10-story hotel. Customers from across south, northeast, south, across India, they come and book the hotel at least 1 week in advance before the festival starts. At least 4 to 5 days before the festival starts, they come and book the hotel. You just think that way, okay? And you know very well as a hotel owner, majority of them are South people, okay? And there's a majority of the South people, and North. A few of them are North, and something like that. You can well, let's say South and North, okay? So what you do is you go by. You have 10 stories are there. You offer a complimentary breakfast. You offer a complimentary breakfast, and each floor you have at least 17 rooms are there. Each floor you have 17 rooms are there. So you want to understand, okay, what do the customers feel about the complimentary breakfast in terms of the quality, taste, everything. What you do is, instead of sending your person to run a survey to each and every floor, you take the entire first floor or any specific floor and you send a person there. Ask each and every roommate, 17 roommates, you need to run a survey and get the data. That's all. Okay, this is another scenario where you can use cluster sampling. Okay. So you have 17 rooms. You remember that. In this case, almost obviously, right? People from South and North also. We have a mix of, the different regions also will be, occupied in the first floor itself. Okay. So in that kind of situations, you can go for cluster sampling. Asking any other examples for this. Okay. One second. Okay, any other example? Like, let's you want to run a customer satisfaction survey for a large retail chain with stores spread across the country. So in that kind of situation, you can employ cluster sampling. Okay, within India, you can take the few specific cities, right? Or you can randomly select few stores as clusters, few stores as clusters, or within Chennai, right? Within Chennai, you can randomly select a few stores as clusters. Okay, and let's say cluster 1, cluster 2, cluster 3. And then survey all customers who visit those selected stores during a specific period to gain insights into customer satisfaction for the entire retail chain. Okay. So in that kind of situation also, you can go for cluster sampling. Okay. In this kind of situation, you can save cost and some extent time also, because you are grouping set of retail stores in a cluster, right? In the some location. All the stores in some location, you are grouping it and you are doing it. In that kind of situation also, you can go for the cluster sampling. And what are the sampling techniques to avoid? The convenience sampling and judgment sampling. These are very biased one. But for you people to understand what are the different sampling techniques, I just mentioned this one also. And I wouldn't recommend to use this kind of technique. Okay, don't use this kind of technique. Next one is sampling distribution. Now, so far you have understood what is population and what is sample. Sample is a subset of your population. And within the sample, right, we have understood what are the various techniques so far. And now let us take a look at the sampling distribution. What is sampling distribution? It is a key concept in inferential statistics. Okay, it represents the distribution of the sample statistic across all possible samples of a given size from your same population. So what does this exactly mean? What does that mean? Sample here, distribution of a sample statistic across all possible samples of given size from a population. This is a very important concept. You need to be aware of this one also. For example, for the sake of simplicity, I'm going to, this is my population. My population, I have only 4 values are there. For the sake of simplification, in the population, I have only 4 values are there. What is the mean value of this one? The population mean is represents mu. It is a parameter. 1, 2, 3, 4, 2.5. Right. So 4 plus 3, 7 plus 3 is 10 divided by 4 is 2.5. The population mean is 2.5. Very good. Now what I do is, what are the possible combinations that we can draw samples in this population? For example, here, I want to, so here you are given an opportunity to draw sample with replacement. Okay. The central idea of this one is, right, we want to take multiple randoms from the same population and calculate the statistics for each sample. The distribution of, those statistics will form the sampling distribution. That's it. Okay. So here, what are the possible combinations I can, let's say, I want to draw multiple samples. What are the possible, let's say if the sample size, each sample size is 2. Let's say each sample size, x1 bar is 2 and x2 bar, x1 bar, x2 bar, each sample, I want to draw as many samples as possible. How many possible combination of samples we can draw? Let's say, given that, each sample size is 2. Okay. Each sample size is 2. And how many, how many samples, how many possible combination samples we can draw here? With replacement, 1, 1, 1, 2. See, 1, 1, 1, 2, 1, 3, 1, 4, right? 1, 3, 1, 4. And what is the mean value for this sample? This is my, I'm going to say x1 bar and x2 bar, x3 bar, x4 bar. This is very simple concept. Please concentrate here. So 1 plus 1 divided by 2 is 1 only. 2 divided by 2 is 1. 1 plus 2 is 3. 3 divided by 2 is 1.5. And 1, 3 is 4 is 2. And 1.45, 5 divided by 2 is 2.5. What are the other possible combinations? These are called your sample means. This is where x1 bar, x2 bar, x3 bar, x3 bar. So x1 bar is nothing but first sample mean. See, x2 bar is second sample mean. x3 bar is third sample mean. Similarly, 2, 1, 2, 2, 2, 3, 2, 4. 2, 2, 2, 3. 2, 1, 2, 2, 4. Right? So what is the mean here? So 2 plus 1, 3. 1.5 and 2, 2 is 2, 5, 2.5 and 6, 3. And similarly, 3, 1 and 3, 2, 3, 3 and 3, 4 is 2 and 2.5 and here 3 and here 3.5, right? 3.5. And similarly for 4. So 4, 1, 4, 2, 4, 3 and 4, 4. The mean is 4 here, 3.5, 3 here, 2.5. So the distribution of all these samples means is called your sampling distribution. So these are called means, sample means. The samples means also called as statistics, right? That is what statistic. We discussed about statistic. Okay, so we have calculated the statistic for each sample, which means the mean in this case. The distribution of these statistic are called the distribution of these statistics form the sampling distribution. If you plot it here, right, instead of specifying each and every value, so 1, 1.5, 2, 2.5, your population mean is somewhere here, right, 2.5, and listen to 2.5 for this sample is falling exactly in the middle of your population mean, and here you have 3 and 3.5 and 4 and what else, right? The distribution of the sample statistics are called your sampling distribution. It's it's as simple as that one. So what is sampling distribution? It is the distribution of each sample's mean across all possible samples of a given size from a population. The given size of the population size is, sorry, the given size of each sample is 2. So here each sample size is 2, right? 1, 1, 1, 2, 1, 3. So overall we have 16 statistics. So sorry, here 1, 2, 3, 4, right? So 4 plus 4, 8, 8 plus 8, 16. 16 statistics are there. So the distribution of the sample means is nothing but sampling distribution. We need to be aware of this one. Anyhow, we are going to discuss it a little later. Don't worry. Next one is the central limit theorem. I'm going to talk about the important concept called central limit theorem. So what is central limit theorem? In statistics, this is one of the important concepts. The central limit theorem, it states that regardless of the shape of the distribution, the sampling distribution of sample means approaches a normal distribution as the sample size gets larger. So here, right, again, so there is another version of the central limit theorem. Okay, as the sample size increases, the distribution of the sample means approaches a normal distribution with the mean nearly equal to population mean and standard deviation equal to sigma n. Okay, and also the another rule is as the sample size increases to, as the sample size increases to 30, it becomes approximately normal distribution. So what here he says is, this definition, what it says is, so here your normal distribution, we already discussed about different types of distribution: normal distribution, uniform distribution, skewed distribution, random distribution. Okay, random distribution, something like this. Okay, and normal, uniform, skewed distribution. Always, this is your right skewed distribution. Okay, these are okay, right, something like, or this is exponential distribution. So each and every population distribution, when you take the population data and if you plot it, for this population, it's a normal distribution, it's a uniform, skewed distribution, then this is exponential distribution, something like that. But when you draw sample 10, irrespective of the shape of your population distribution, you will find something like this, right? So look here, it is not showing anything good, right? It's something like a triangle. But when you draw sample somewhat close to 30, irrespective of the type of your population's distribution, it becomes approximately normally distributed. It becomes approximately normally distributed. So how is it possible? How is it possible? Is it possible? For example, I just show you here with this data already, I have it. Look here, in this case, if I take only these 3 values, this is my, okay, I'll just remove this chart. Let's say you have a population, but make sure that when you draw a sample, you're drawing the sample from the same population, okay? If your population is this one, you need to draw a sample from this one only. If your population is this one, you need to draw a sample from this one only, okay? So your sample is supposed to be from the same population. And here, let's all these values are falling in this. Let's assume that in the normal distribution, this is a normal distribution. So what I do is I just draw 3, 5, 8, and 10 only. They say this is not a population, actually, it is a sample only. Your population will have some more data. Let's say we start with, initially we started, drawing few samples, 4. And then what I do is I just go here, insert, and I'm going to create a histogram to view whether it's a normal distribution or not. Here I just go here, insert, and I just select this one. I'm going to use it. Is this a normal distribution? No, right? This is not a normal distribution. What I do is I'm going to draw, in addition to this, I'm going to draw some more sample from a population. And then what I do is I'm going to select the data from this one. I'm going to increase my sample size to, I'm going to increase my sample size. One second. In this case, let me select the data. Okay. What I will do is, when I selected this, it was not a normal distribution. Let's assume that this is my population, okay? And in this case, I'm going to take some more data. Okay. What is wrong with this? It was showing correctly here. Okay, I have taken from here, okay, not this one. 6.5 and 10, 17.75. And for this one, okay, we will, okay, I think in this case, I've taken the data from here. Up to Q12. Okay, this is the one I've taken it. Okay, for this one. In this case, for example, if I take a few values here, and then if I go and select it here, it will be something like that, right? So if I select only these three values, what is going to happen? The whole idea is, as you increase the sample size, it will become approximately normally distributed. That is the whole idea here. That this is the one, right, found out by someone, right, some scientist. It's really helpful. How it is helpful, that we'll discuss it, as part of the confidence interval. There is something called confidence interval. Look here, as you draw more samples, it becomes approximately normally distributed. But in this case, when you select only three records, instead of this, if you select up to this one only, it is not normally distributed, right? As you draw more samples, it becomes approximately normally distributed. And what central limit theorem says is, if you draw a sample, as you draw a sample close to 30, irrespective of the shape of your population distribution, your sample will become approximately normally distributed. Let's say, your population distribution, uniform distribution. When you draw a sample 10 or something, it will not be, that good. And when you draw somewhat closer to 30, it will become approximately normally distributed, irrespective of your population distribution. When you draw a sample, when your sample size is 30, it is going to be approximately normally distributed. That is what this theorem tells us. So that's what it is. As the sample size increases, the distribution of the sample means, the distribution of sample means, this is another thing, okay? The sample means approaches a normal distribution. The sample means also approaches the normal distribution with the mean nearly equal to population mean and standard deviation equal to sigma divided by square root of n. So, okay, what I will do is, I will just show you with this example. So what you need to remember is, so these are like your sample means, okay? When you plot your sample means, it will become approximately normal. This is one point you need to remember it. Apart from this, look at this as these values are from your population. Like I wrote it earlier, right? If you draw a sample size 2, what are the possible combinations how many possible combinations you can draw sample here? You remember it in the PowerPoint I have shown you, right? 1, 2, 3, 4. So 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, right? So likewise, how many samples we can draw? 14 samples we can draw here. 14 samples we can draw here. We can draw 14 samples. Each sample, we compute the mean and then we note down the mean. When you plot all these means, sample means in a distribution, that is called your sampling distribution. When you take an average for the sampling distribution, you are getting 2.5. Your sampling distribution's mean value and your population mean value same. This is what this is also one of the central limit theorem, one of the principles of your central limit theorem. Whereas the means of all the means of your sample distributions mean is equivalent to your population mean. It is as simple as that. See, if you ask me to draw a sample again, right? So here with replacement, let's say I want to draw, let's say my sample size is 2. With sample size 2, how many number of possible combination of samples we can draw here? So 1, 1, 16, right? 1, 1. And other sample is 1, 1. So 1, 1, 1, 2, 1, 3, 1, 4. 1, 2, 1, 3, 1, 4. What does it mean for this is sample 1, sample 2, sample 3, sample 4. Right? And the next one is 2, 1 and 2, 2, 2, 3, 2, 4. Guys, this is the very simplified version. If you see it in the internet, you will get confused literally. Okay, you will understand, but it takes a lot of time, right? So 2, 1, 2, 2, 2, 3, 2, 4. And next one is 3, 1 and 3, 2 and 3, 3 and 3, 4. And similarly, 4, 1 and 4, 2 and 4, 3, 4, 4. So how many samples we have? 16 samples. Each sample, if I compute the mean, how many means I will have it? 16 means. Already I did it. To make your life simple, see, for each sample, I computed the mean. And again, I'm taking the mean on all these samples mean, 2.5. This 2.5 is equivalent to my population mean. This is my mu. This is my population mean. This is my sampling distribution mean. Here they use different notation. X bar is sample mean. Sampling distribution mean is SX bar, I think so, right? So this is 2.5. So your population mean is equivalent to your sampling distribution Xi, your sampling distribution mean. That is what it tells us. If you go back to the theory here, the definition, as the sample size increases, which means, right, let's 30, the distribution of the sample means also approaches a normal distribution with mean nearly equal to population mean and standard deviation equal to sigma equal to, the normal distribution mean nearly equal to population mean. The sample means approaches a normal distribution with mean nearly equal to population mean. That is what it tells us. So here, right, regardless of the shape of the distribution, the sampling distribution, sample means approaches normal distribution. But here I have elaborated this in detail. So the population mean is equal to standard, the population mean is equivalent to your sampling distribution mean. And at the same time, your sample means will approach a normal distribution as the sample size gets larger. So in this case, what happened? In this example, okay, I did something nonsense here. 1 second. In this case, I have taken a few samples here. In this case, okay. So in this case, I have taken few samples here. So here I have 3, 5, 8, 10, 12, right? In this case, what I did, what is the population mean here? The population mean is 13.8. Average is this one. Let's assume that this is my population data. And then here it comes around close to 14, right? If I do 14, and if I draw 3, 5, 8, 10, if I, what is the average of this one? We can see that average is 6.5. That's what I put it here. If I draw a sample, first sample, 6.5, and then if I take 5, 8, 12 in another sample with a replacement, sorry, 5, 8, so in this case, 5, 8, and 12 and 15 I have taken. In this case, the average is 10. Okay. Likewise, I have taken, different, okay, I just put it here so that you'll be able to understand. And here I have taken 3, 5, 8, 10 as my sample one. In my sample one, I have taken this value. Okay, so for example, here 3, 5, 8, and 10. I have taken this value. And the next one is 5, 8, 12. 5, 8, 12, 15. And 8, 18, 20, 25. So for this is the average. So in this population, I have randomly sampled the data. These, and randomly samples. This is sample 1 and sample 2, sample 3. I randomly sample the data and computed the mean for each and every sample. When you plot these, the sample mean, when you plot the sample mean, it becomes approximately normal. Okay. So we have randomly sampled the data from the population and I calculate the mean for each sample. Okay. And then what we did here, with this 10 data points in the population and the small size samples, right? 4, each sample size is 4 only. You can see, some kind of normal distribution here, right? The sample means of the sample means when you plot it in a chart, as you, for example, if I plot only few samples here, sample means. Only few sample means, it is not approximately. As you draw more samples, it becomes approximately normally distributed. So this one relates to my first principle. What is my first principle? As the sample size increases, your distribution will become, approximately normal distribution, especially irrespective of the population distribution. When you draw a sample which is closer to 30, it will become approximately normally distributed. Okay. When I draw random samples from the population, and then when I plot these samples mean in the chart, it becomes approximately normally distributed. As the number of samples increases, the sample means, if I increase the sample size, number of samples, and each samples means when I plot it here, as with the more samples means, it becomes approximately normally distributed. Apart from this, the sampling distribution mean is equivalent to the population distribution. Sorry. Yeah, as the sample, irrespective of the population distribution, if the sample size becomes 30, it will become normally distributed, property 1, and that is what it is, right? And the property 2 is when the sample means, right? The sample distribution of sample means approaches a normal distribution as the sample size gets larger. That is what this example, okay, that is what this example tells you. Okay, with 3 samples, means if you plot it here, it was not normally distributed. I increase the number of samples. 6 with 6 samples means when I plot it, it becomes approximately normally distributed. And another point, what he says here is, as the sample size increases, the distribution of sample means approaches normal distribution. Yeah, it talks about sample means only, with the mean nearly equal to population mean, and the standard deviation equal to sigma divided by square root of n. The sampling distribution mean is equivalent to your population mean. Okay, that is what we have seen it. And at the same time, your population standard deviation is equivalent to your sampling distributions, standard deviation. How do you find out the sampling distribution standard deviation? Sigma divided by square root n. Sigma divided by square root n. This is called your error. How far each value is away from your mean. That is what your standard deviation. So here, okay, now the question is, why do I need to learn central limit theorem? See, in this case, we have drawn many samples, right? Look here, if you see here, here in this case, so forget about this case. If you look at these 4 values, this is my population values. In my population, let's say hypothetically, I have only 4 values. To draw sample size, let's each sample size 2. And if I wanted to draw, if the sample size 2, how many possible combination sample we can draw? 16 possible sample. In this case, you need to draw 16, all the possible combination samples, and you need to find out each sample's mean, and you need to take the mean of all the samples mean. Do you think it is practically possible in the real-time scenario? In the real-time scenario, do you think in the population we have only 4 values in it? No, right? In the population, we have huge volume of data. Okay, you cannot draw all possible combination of samples from your population. Okay, we never actually create a sampling distribution that would require a huge effort since we cannot afford to take multiple samples. So what we do, based on a single sample, is it possible to make inference about the population mean? That is where, the mean. So that is where there is something called confidence interval estimation and hypothesis testings are coming into picture. Okay, based on a single sample itself, is it possible for me to make an inference about the population mean? That is where there is some, yes, it is possible. That is where there is a concept called confidence interval estimation and hypothesis testing comes into picture. These are the engine driving, so the engine that drives these tools like confidence interval estimation, hypothesis are called your central limit theorem. You understood, right? Instead of drawing all possible combination of sample from a huge population, it is practically impossible. Is there any way can I use a single sample to make an estimation about the population mean? Yes, that is where we have some other technique called confidence interval comes into picture. The engine driving this confidence interval is nothing but your central limit theorem. With this, I'm going to stop. As of this one, the confidence interval, we'll discuss it in the next session. Okay, next week and we will continue. Next weekend, we are going to increase the duration also. That I will get back to you about the timing of obviously, if I start by 9 p.m., it will be too late. We'll get back to you about the schedule, everything. Okay. With this, I'm going to wrap up. Before I wrap up, a quick summary about what we discussed. Okay, we discussed about what is inferential statistics all about. And also I discussed about what is population and what is sampling. And also we discussed about sampling distribution. And also I discussed about the central limit theorem. Okay. And different types of sampling technique also I discussed. Followed by that, we discussed about the central limit theorem. Any questions so far? Okay, since you don't have any questions, I'm going to wrap up the session. You need to watch my video. So it is not that they blindly came up